Okay, go ahead.
So you see the title. The next figure is, the next folio is the introducing of myself, my home page, and then my titles. And you see, as the last title was Professor on various universities of applied sciences in Germany. And then if you want to know more, then you can show my homepage. So now let us see what about. I have not much to present. I have 30 folios and I will try to do it more or less rush. So the Newton's law of motion is of course known, and the third law is for every action there is an equivalent opposite reaction. It is of course known, it will be used, and of course it is also a figure. This is the action, for example, F12, and there is a reaction or an opposite is the same. The many things is, the important things is that there are also always, there are two members, the action and the reaction. And the same principle was used by anti-system-approach. Namely, you see in 1968, it was a first publication, and the publication was devoted to defining of transfer function of multi-stage systems. And it is a page of the publication, and the main idea was how to reduce the dimensionality. And the triggering for this work was Bellman's dynamic programming. As you see here, we have n stages, and each stage has also many variables. So such a problem, such a solution, such a problem is very complicated, and Bellman proposed one method called dynamic programming, but this method works efficiently only by n equal 2 state variables. By 3, 4, and so on, as Bellman itself says, it is shown exponentially rise, and he called it curse of dimensionality. And it was exactly the problem, how to solve this dimensionality problem. First, this publication has shown that it is possible to build a weighted sum of variables. As is shown here, xe, for example, one vector here, our output is equal operator multiplied with x for input. Also, output is equal operator multiplied by our input. They are vectors. And now the method was to build some product, some weighted sum by each stage. That means, for example, here one stage, or here one stage, and so on. Here is here. In this case, if we build such sums, then we have that between stages, the E variables, they are scalars. Originally we have vectors, but they are scalars. And the scalars are equal through the whole line, through the whole system. So that means we have by input n variables, by output n variables, by in between we have only one variable. And it is important these variables equal on each stage. It is very unbelievable that we can such a combination, but it is of course possible. The problem is how we can extract by output the variables. It is clear, mathematically it's clear that to build the sum is no problem, but the problem is to extract from the sum the variables. So it was the problem so formulated, and then come the idea to each variable to give some feature, some property. So it is shown here. We build the sum of variables, and now we want to extract And if each variable, for example, has a color, in this case, it is clear we can also recognize through the color, which variable it is. But to explain this process, we should go to symmetry. So the symmetry has a long history, and the symmetry is very important, and we can find symmetry everywhere if we know how to look for it. And these works show different applications of symmetry, and important is the next page by antisymmetry. And the antisymmetry is like a symmetry, but with the opposite sign. So we see that the antisymmetry, what is symmetry is very well known, but what is antisymmetry? It is the same symmetry, but with a negative sign. There are common applications, and here are also special funny applications from Jean Siroir there. He has a very interesting work, and this work was used, I used it also in my book, and I used it for automation and electrotechnic. And what is shown here that we have, if we go through these figures, then we have by each figure some of antisymmetry. Namely, something will be changed. For example, here is changed color, here is changed the position, and so on. The same is by this circle. I don't want to review now the book. I only want to say how follows the definition of antisystem. That means if we have a system A, original system, here is two variables, then always exists one system which is called antisystem, and it is the same A, mathematically is transposed, and the system has variables W. So we have practically original system with inputs Y and antisystem with inputs Wx, because it is now on the right side. As far is nothing known. It is possible to think, but if we multiply this vector, I show now this vector, we multiply with this vector, and then we get it is shown, it is scalar work. Then we get some scalar value. This scalar value is shown as Ax, x side. And then we will multiply also this one, this two, this vector with this vector. Then we will get Ay. So of each side of the system and antisystem, of each side we have these variables. These variables we can call energy or intensity or variable compression, how we want. But the important is that the same how we choose these variables. I will delete it. Want to delete? Okay. If we choose these variables, what is it here? No, I want to delete it. Okay, if we choose these variables, W, the same which value we choose of W input for antisystem, the balance will be all given. That means that this equality, this is not dependent of the value of W. We can choose arbitrary values. And it is very important for this anti-system approach. How we can use it? We can also prove it, of course. Here is, for example, shown a model. We have an input of the system on the left, and we have input of the anti-system of the right. And if both systems, GS and GM, are equal, in this case, we can change this input of anti-system. And by each value of input, we get here both values equal. So on this point, we have a first question. this balance, is it mathematically correct or it is proved? The answer is yes, it is mathematically correct. It is very easy to show. And it is also proved, for example, by simple simulation. When we have here system, here on the right anti-system, and if we put here some disturbance, the disturbance means that the anti-system on some time, very small time, differs from system. That means here system and anti-system are equal. Balance is here. But if they are not equal, then we have the disturbance. In other words, the peace is when both systems are equal, and when they are not equal, then we have some disturbance. So the first question, is the balance really? It is yes. Then we have the next question. How we can use it? For what purpose? My whole presentation is the answer of this question, but because I begin to answer, I want to show you one example from 1936 from one physician called Luke, and he has promoted some method how to damp the noise. Okay, this is a model. You see already the left is system, right is the anti-system, and here is shown the damped noise. It is, I hope it is clear. Then in this area is noise here because the system and anti-system are not equal, but begin from 10 seconds, the both are equal and the noise disappeared. It is very interesting. We have really noise, but the noise will be damped by the anti-system. This method was used 2001 in Frankfurt Airport, on some airport, was really used to damp the noise of the aircraft. And here is shown how it was done. And also we have here also a simulation with Simulink. So that means beginning from 1936 or maybe earlier, the idea of action between system and anti-system, it was known, but it was not formulated as an anti-system approach. It was some, and there are also known other methods. Let us go to our approach, namely how we can use it.
Dr. Serge, we still have 1 more minute, so just okay. 1 more minute. Yeah.
How much? 1?
1 minute.
Okay. Then I will shortly say, because you can see my presentation later. The following. If we can choose the vector of anti-system, then let us choose so that we have some advantages. It is shown in the whole presentation how to choose the anti-system variable, for example, orthogonally or so. And then we can build the systems and solve the system because they are very easy to solve as an original system. So the main idea is to use the anti-system instead of system, but in this way that the anti-system let us to get a solution very easy. And now let us go through all pages. They are, for example, one example, and then we have simulation. We have another example, and simulation, and results. And all these books have some about this anti-system approach. Each book has some chapter, and also it was by exhibitions in Germany. For example, software agents, neural password, or also anti-neurons, and the electrical circuits. You see here on the left the original, and down is anti-system. And so we go through closed loop applications, very special applications. I have no time to explain it, but you will see in each page you have system and anti-system, and you have also the balance. So I think Dr. Elbakil, I have 1 minute used. So thank you for your attention. And if you have interest, then show my presentation. And then you can ask, or you can also now give a questions. Thank you very much.
Thank you so much, Dr. Serge.